Si pueden acercarse a sus lugares, por favor. Muy buenos días. Vamos a iniciar con la parte científica del Simposio Internacional en Métodos Matemáticos Aplicados a las Ciencias. Es un gusto presentarles a la doctora Kimberly Villalobos Carballo, quien obtuvo su doctorado en investigación de operaciones en el Instituto Tecnológico de Massachusetts, MIT. Posteriormente enseñó Machine Learning under Modern Optimization Lens en el MIT y desde enero de 2025 comenzó como profesora en la Escuela de Ingeniería de la Universidad de Nueva York, NYU. Su investigación integra la optimización y Machine Learning para desarrollar algoritmos que abordan desafíos prácticos como trabajar con conjuntos de datos pequeños y satisfacer requisitos computacionales. A Kimberly le apasionan especialmente las aplicaciones en el ámbito de la salud y gran parte de su investigación ha sido inspirada por colaboraciones con hospitales como el Brigham and Women's Hospital, Hartford Healthcare y UMass Memorial Health. Antes de comenzar sus estudios doctorales, Kimberly se graduó con honores del MIT, donde obtuvo un doble título de grado en Matemáticas y Ciencias de la Computación. Fue olímpica en Olcoma y es un gran orgullo nacional. Me honra presentar a Kimberly Villalobos Carballo.
Thank you so much. What nice words. It's such a great pleasure to be here with you all and to be presented in my home country. That's amazing. I'm very excited to be sharing my most recent work with all of you on feature selection for machine learning with unstructured data. And even though the framework I'll be presenting is quite general across disciplines, I'm going to be talking primarily about healthcare because that's my main area of research. So maybe to begin, I'd like you all to think of a time when you went to the hospital, when you were admitted to the hospital or someone you know, and let's try to think about all the data that was collected throughout your hospital visit. So probably one of the first things that people collect is your demographic information or tabular data that can be put into a table. This is what we call structured data. Probably as you go, the doctors are going to gather some of your vitals, some of your laboratory values, which are time series modality data. Depending on the condition that you have, then probably you're going to need some imaging, X-rays, ultrasound, MRIs, vision data modality. And throughout all of your stay, there's going to be people taking notes, right? You're going to have the nurses in the emergency department writing language, the doctors write notes, the radiologists write reports. And all of these multimodal data is what the specialist that is going to see you is going to use to analyze your case, right? So they try to use both structured data, which is the one in which each column represents the same for every data sample, as well as unstructured data, right? So if we think, for instance, of language, thinking of the ith character, the ith word, or the ith sentence, it does not necessarily mean the same across data samples. So healthcare, as it is intrinsically multimodal. It leverages all these different modalities of data to be able, the physicians use all these modalities of data to be able to make a holistic assessment of your case. Now, if we think of machine learning for healthcare in the past years, we have seen that even though since many decades ago, tabular data, structured data has been used for predictive analytics, in the past 5 years, perhaps, the development and the advancements in unstructured data, images, and language has shown remarkable improvements in predictive performance. And there's a lot of people working on this area, but just to mention some examples, in some of my work, we've used all the information that we have in all modalities for diagnosis prediction, for patient flow predictions. In one of my most recent works, we used all these modalities to predict victims of domestic violence from electronic health records, even years in advance. So it all looks really good, and it seems like all this data really has capabilities to improve predictive power of machine learning. But there is one big limitation, and is that once you include unstructured data, your models lose all sort of interpretability and explainability. And this in healthcare is particularly important because you're not going to find a physician that is going to use your models and not understand why your model is predicting what it's saying. So perhaps in some other applications, like financial applications, it doesn't matter too much if you know why the prediction is happening, so long as it's correct. However, in healthcare, it really is a necessity to be able to understand why the model is predicting what it's predicting, as opposed to just having good accuracy. And interpretability is not only important for the physicians to want to use your models and for you to be able to deploy it in practice, but actually it's also very useful for quickly identifying mistakes, right? So no machine learning model is perfect. We never achieve 100% accuracy. And if someone is using your model and the model is making a mistake, they're not going to be able to know quickly that the model is making a mistake, in which if you provide some sort of verification or some sort of explanation of why the model is making that prediction, potentially you could also improve the decision-making part, because physicians can quickly identify something is wrong, okay? So in all the collaborations I've had with hospitals, it's very funny because doctors really, really like decision trees. You can have the most complicated neural network, you can use your favorite deep learning algorithm, whatever processing you want. They want to see a tree. They want to see something they understand that they can easily use and they can just follow along. And that's because trees are the most interpretable models we know, right? Even though the predicted performance may not be the best when we're dealing with nodes or with images. And even defining a tree from language may not be obvious. And something that is also really important about trees is that not only it allows to interpret the predictions, but also it allows to generate hypotheses for causal factors. So even though not everything that shows up as predictive factor may be causing the output, it does allow for generating all these hypotheses so they can be further tested. Now, feature selection and feature importance have been two very important tools in machine learning to improve interpretability of the models. So if we think about feature selection first, which refers to finding what are the parts of the input that are driving a prediction, this has been very helpful for, first of all, reducing computational expense, because you don't use all the data that you have, but only the important bits. It's also very useful for facilitating evaluation, because you can exactly pinpoint what parts of your data contribute to the output that the model is making. And it's very useful for designing interventions because of the hypothesis generation of causal factors. Feature importance is also very relevant when it comes to interpretability. The main difference is that in feature selection, we want to find a small subset of features that are the only ones that are going to be used for prediction. Whereas in feature importance, it doesn't matter how many features you used. This is kind of like after the fact tool in which you try to quantify how much each specific part of the input contributed to your final prediction. This has been also very useful for interpretability. Many of you may be familiar with Shapley values or permutation importance, in which you try to quantify how much each specific column in your table contributed to a prediction. And some of this has been extended to some of the deep learning work on unstructured data. Now, what is the problem? The problem is that there is a lot of feature selection and feature importance algorithms for tabular data, but they do not work for unstructured data. So even though there is some very remarkable multimodal machine learning models in healthcare and across other disciplines, they're not to this day deployed so commonly in practice, because physicians cannot understand what these models are predicting. So even if my model, once I put X-rays and MRIs and clinical notes, is performing better, I am completely disrupting the interpretability and explainability component of my model. So physicians just want to go back to their trees, okay? So the main question that I want to address in this talk is, how can we perform feature selection and feature importance in a little bit of a rigorous way when it comes to language or images or videos that are unstructured? So for the talk, I'm going to start with a little bit of background on the feature selection problem. Then I'll discuss the approach that we have to address this problem, some results, and then finally the conclusion. So there is a lot of work on both feature selection and feature importance that already exists primarily in the context of tabular data. So there is a lot of discrete optimization works in which you try to introduce binary variables to select or not select a column in a table, and then you develop an algorithm around that. There are a lot of sequential search algorithms in which you try to find what's the most important variable, conditional on that, what's the next important variable, and so on and so forth. A lot of random search algorithms in which if you want to identify the best subset of features for your predictive model, because this is a combinatorial problem where you have to find over the space of all subsets, random search can be very useful to just kind of randomly search, see if you get lucky finding importance. And then, of course, some regularization techniques like lasso and some other penalties that you can put in the objective that you're minimizing as to promote that not all your variables are used, but only a small subset. But again, the top three here only have been applied to tabular data. Regularization you could put in deep learning and some of your multimodal machine learning models, but this does not allow you to exactly select 5 or 6 sentences or features that are important, but rather is just something that helps the model use less, but you cannot control how much it's using. Similarly, there's been a lot of works on feature attribution. Perhaps the most popular ones are the additive feature attribution models like Shapley values, as well as a lot of gradient-based methods where even though you may have a very complicated neural network or deep learning model that is taking inputs and then giving you outputs, you can use somewhat like the gradients across the model to try to understand where is the model putting most of its attention or its weights with respect to the input. But these are kind of like heuristic methods that still do not guarantee those are the most important ones, and that if you only use those features, you would still have good performance. Attention score, so if everyone here is using ChatGPT or some sort of large language model, because these are so big, the kind of like the heuristic that people have gone to is attention scores, where you try to see where is the model paying attention to, but this does not mean that those are the most important features. And some other works that I'm not mentioning here, but that again are primarily focused for, the rigorous ones are primarily focused for structured data, and there are some heuristics for unstructured data. All right, so in case you're not familiar, I'd like to go through what's the general pipeline of how currently a machine learning model is trained on unstructured data. So here I have an example of a medical note with some information of a patient. In the modality here is text. And suppose that we want to train a machine learning model where our data points look like this. So the standard practice is to use some sort of encoder function that allows you to map this text to a vector of fixed dimension. Which encoder you use, there's a lot of ways to do it, but you want some function that allows you to map unstructured data to a fixed dimensional vector space. Once you have your vector, you train your machine learning model of preference, neural network, tree, anything you want, from that vector space to produce the prediction that you want. Okay? So this is the general pipeline. Nowadays, this encoder almost always is a large language model. So something like ChatGPT that is used for generating text, but that you can also use it just to encode data, not just to generate data. You can use it to just do this mapping from text to a fixed dimensional vector space. So given this pipeline, there are 3 main challenges to doing feature selection, as we're thinking. So the first one is that there is a disconnect between interpretability in the note and the vector that the encoder is given. If this encoder is a function parameterized by billions or trillions of parameters, it's really difficult to map back what each component of the vector in the encoding has to do with any interpretability in this node. It's really hard to keep that mapping because it's just such a complex function. The second challenge is the lack of structure. So as I was saying, we do not know that the third sentence in this node is talking about the same thing across patients. They can be completely different things. So I cannot make assumption on order or structure like we do with tables. And the third challenge is the high dimensionality of the data. This is a very short node. In practice, you usually have extremely large texts. The encoder has billions of parameters of variables that you have to find. The model that you usually use for machine learning, if it's a neural network, is going to be extremely complex. And that means that not only we have to come up with a way to to solve 1 and 2, but also we have to do so efficiently. Okay? So there are 3 research questions that we're going to address in this project. The first one is, how can we do feature selection in a tractable way in predictive tasks that have unstructured data? And I'm going to be using in all the experiments text data. The second research question is, what is the effect of feature selection on predictive performance when we have unstructured data? So feature selection from tables, you can show that actually in many occasions, it improves predictive performance, because you are kind of like, if you have some columns in your table that are irrelevant and they're just adding noise, you're better off not using them. And so feature selection actually tends to do some sort of regularization. But we don't know that that would still happen in the case of unstructured data. And the third research question is, can we actually identify meaningful predictive factors, in a clinical sense, meaningful, from unstructured healthcare data if we do feature selection? Okay, so the main idea of how we're going to perform feature selection from unstructured data is the following. So the first part is that to do this first encoding that I talked about, where we have some text, we have a this encoding is also called embeddings, if you're not familiar with it. So the main idea is that I'm going to use a large language model to do this encoding. There are several reasons for that. The first one is they're just the best technology right now for processing language, and I cannot deny that. And the second one is that these models, because they've been trained with such big amounts of data, you can use them as a function that already exists, as opposed to a function that you have to find. So just like if I had my input x and I was going to map it to x squared, I just do that transformation. I don't have to find the function. I can do the same with large language models. I can just use your favorite large language model that is available online, take my input and map it to a vector space. I could optimize over this, but that's just going to increase a little bit the computational complexity. But I just want you to think of this encoder as a function h that maps nodes to fixed vector space. So far, I haven't done anything new. I'm just saying this is the setting in which I'm going to be encoding my data, so that now all my input is in a p-dimensional vector space. The second idea, and perhaps the more interesting one, is we're going to use historical data to train 2 machine learning models simultaneously. I have my predictive task that I want to solve, and let's think about classification for now. Let's say that we want to predict mortality risk for a patient. And let's say that this is all the data I have. So the standard way would be I use this data, I encode it, and then I train a machine learning model F that gives me a probability of the outcome occurring. But what I'm going to do is that I'm going to introduce another model called G, which is also going to be trained from this historical data. But the task of this model G is not mortality prediction, but rather to find the important sentences in this text. I do not have data for that. I do not have a data set that is labeled to tell me which sentence is important or not. So I cannot do standard supervised learning for this task separately. But what I want to do is I want to leverage the mortality risk prediction task to learn 2 things: the mortality risk prediction as well as the important sentences, and kind of like put the two together in a single optimization problem that I can minimize. So in a way, we can think of model G as giving me a score of how important the sentence or the feature that is coming into G is. Okay, so G is going to quantify the importance. F is going to make the prediction of the risk that I care about. And if we want to put that into a little bit of notation, so we're going to assume we're working with a binary classification problem, and this is just for ease of explanation, where you want to predict a binary output. So does the patient die or not at the end of the stay? And we're going to assume that our input is a sequence of M features, where each feature can be a multimodal input. So the easiest way to think about it is, let's suppose that each data point X is a medical note, and each feature Xi is a sentence in that note. And what I want to do is identify the 3 or 4 sentences in this note that are most important for this prediction. And we assume that we have the target variable y, which is what we want to predict, 0 or 1. Here we have our encoder function h, which, as I said, maps any subset of the features, so not just a single sentence, but any subset of the features S is going to be mapped to a fixed dimensional vector space of dimension P. And LLMs are really good for this, because if I take one sentence and I encode it with ChatGPT, let's say, it's going to give me a p-dimensional vector. If I take 3 sentences, it's also going to give me a p-dimensional vector. So it's kind of like a very useful tool to map any length text into a fixed dimensional vector space. Then I'm going to have my predictive model F, which is going to take that p-dimensional vector data point and map it to a probability between 0 and 1, which is going to be interpreted as the probability of the outcome occurring, in this case, the patient expiring. And lastly, we have our selection model G. So G also operates on the p-dimensional vector space, where G takes the vector representation of a set of sentences, and it's going to output a score of how important that, that input is. So this is the notation, and now we have to figure out what is the optimization problem I want to solve such that F and G actually learn what I want them to learn. So the first thing is I want to compute the probability of selecting, I want to model the probability of selecting a specific feature, let's say the ith feature in this data point. So for the ith sentence in my note, I want to be able to model the probability of selecting that sentence in my feature selection problem. And to model that, I'm basically going to take my encoder H, encode the xi feature, so this brings me a p-dimensional vector, and then apply G function to that. So G of H of X of I is going to give me the score for the ith sentence. And then I'm just applying a softmax transformation to make sure that my scores across all the possible inputs sum up to 1, right? So I'm just taking the exponential and divided by the sum of the exponentials. But if I sum across all the i's, this sums up to 1. So I have m different values between 0 and 1, summing up to 1. I can interpret them as the probability of selecting each ith feature. And I'm going to call that GI. So if I model the probability this way of selecting the feature, I also model the probability of the task that I care about. And that is my model F, which is the predictive model. So F also just takes the ith feature, encodes it with H, and then outputs a probability, F of H of Xi. So far, all I'm doing is modeling how I'm going to represent the probability of selecting a specific feature and of the predicting the positive class, so mortality, for using only a specific feature. But this is conditional. This is that I only use the ith feature, this will be the probability. So if I have these two definitions, I can now compute what is the likelihood that I make the correct prediction for the nth data point, given my functions f, g, and h. So if I already have fixed my functions f, g, and h, the probability that I make the correct prediction for the data point n can be written in the following format, and maybe I'll just try to go through it. So there's two cases, right? My nth data point can have yn equal to 0 or yn equal to 1. So the patient dies or doesn't die. Let's suppose the patient dies. If the patient dies, yn is equal to 1, and this is equal to 0, so this term cancels out. I only have this term. And this term is just the total law of probabilities, where I'm saying the probability that I predict 1 is the sum of the probabilities that I predict 1 using the ith feature, given the probability of selecting the ith feature. So this expression here is just getting the probability of predicting 1 using the conditional probabilities on the feature that I'm selecting. And similarly, if yn is equal to 0, then this term cancels out, and I get the probability of predicting 0, also using conditional probabilities. So given that we model the probabilities like we did before, this expression is going to quantify the probability that my F, my G, and my H make the correct prediction for this patient. So to optimize over F, G, and potentially H, what I want to do is, given my historical data, which we can assume has n different samples in it, what I want to do is I want to maximize the likelihood of making the correct predictions across my data. And the expression looks like this. First of all, if we take this and we apply a logarithmic function, this is just because it's easier to take derivatives with logarithms, then we're going to split this product into a sum, and then we can take the exponent down, and then we are just summing this across all the data points. So this expression here, it's what, if you're familiar with log likelihood maximization, is just the equivalent under the selection conditional probabilities that we're using. What this means is, in standard machine learning, what you do is you compute the likelihood of making the right prediction, you compute the log likelihood, and you find your F, G, and H that maximize this probability. That's what training a machine learning model means. It means finding the best functions to maximize the probability of making correct predictions. For us, it's the exact same thing, except our loss function has changed a little bit because we're not using the entire input, we're only using one feature of the input, and that's really important. Right now, I'm only selecting one. I'm only selecting one sentence per node. But if I'm only gonna use one sentence per node, this is the equivalent log likelihood maximization problem that I can optimize for using gradient descent or any other a gradient-based algorithm to find what are my best F, G, and H. So I don't want to use just one sentence. I want to find a subset of sentences, 5, 6, 10, I don't know how many, but I want to find, but ideally the best subset of sentences for this prediction task. So what we're going to do is that we're going to use the idea that I just described in a greedy fashion, where we first select the most important sentence, condition on that, select the next most important sentence, condition on that, and so on and so forth. So the algorithm would look something like this, where we start with I1 of n being equal to the empty set. This means what are the set of features for data point n that have been selected. So at the beginning, we haven't selected anything. And then for each iteration 1 to m, which is the total number of features for each data point, we're going to do the following. First, we define our probability of selecting the ith sentence, like we did before, GIN. Then we find the next most important sentence by solving the maximum likelihood optimization problem that we described before with a little variant here. So first of all, the input that the encoder is taking is going to be the features that were already selected, union with the new feature that I'm trying to evaluate. And when I sum over the set of features that have not been selected. So out of the features that have not been selected, I want to find the next best one to add to my set of selected features. Once I do this and I optimize for F, G, and H, I update my set of selected features for data point n to be what I had before, union with the feature that had the maximum importance score in the previous iteration. And I could do this just for 4 steps, if I only want to select 4 sentences, or I could do it for all of it so that I can select actually all the features in a specific order. So far, what I described was for binary classification. We actually can extend to the multi-class classification problem, where instead of having just two possible outputs, 0 and 1, you have C different classes. And it's pretty similar. Basically, the main difference is in the input. Our target vector y is not going to be just a number 0, 1, but it's going to be a vector of C different binary numbers that sum up to 1. So basically, a one-hot encoding where all the vectors, all the entries are 0 except 1 for the class that this data point has. Our encoder doesn't change. the predictive model is now going to give me not just a real number between 0 and 1 with the probability, but it's going to give me a vector of dimension C of numbers between 0 and 1 that sum up to 1 so that they can actually represent the probability. And we still have our selection model. So what changes here is when I want to compute the likelihood of a data point, of making the right prediction for a data point n, I'm going to have this product. So it's the same idea as before. Let's suppose that the nth data point has the correct target for that is little c. So for that little c, all the other products do nothing because they're going to be 0. And for that one, this yn is going to be 1. So I only have one of these products active. And for that one, fc gives me the probability of predicting mortality for that patient using only the ith feature, and then conditional on using only the ith feature times the probability of selecting that feature. So it's just a generalization of what we did before, but instead of having 0 and 1 as the possible outputs, we have a p-dimensional vector with a probability describing the likelihood of each class. And using this, we can, again, apply the logarithmic function and maximize the likelihood across the data set. And this should look very, very familiar with cross-entropy minimization. If you are familiar with machine learning, this is the, minimizing the negative of this is equivalent to the cross-entropy minimization problem, conditional on our selection probabilities. And I do not have it in this presentation, but you can do similar extensions for regression tasks where your output is not with respect to probability of predicting a class, but you just have like the sum of square errors or something like this, where you can still compute these losses conditional on which is the feature that you're selecting. Okay, so this is like a high-level view of the algorithm, and what I want to show you is the results that we've obtained using this framework on real-world healthcare data. So for this first experiment, I'm going to use the Framingham Heart Study. And if you're not familiar with it, I invite you to go read with it. This is a very revolutionary study for coronary heart disease. And the reason that we all go to the doctor and the first thing they do is take our blood pressure and our vitals is because of this study. So this study, which is quite old, was in the Framingham city. And the idea here was they wanted to be able to study patients for a long period of time, we're talking decades, to be able to understand what are the risk factors of coronary heart disease. So for this task, we have a binary outcome. The idea is to predict whether a patient will develop coronary heart disease within the next 10 years. And thanks to this study, there are some very well established risk factors like age, gender, and systolic blood pressure. Those are well known to affect and to be causal for your coronary heart disease risk. There are 3,658 patients that were enrolled in this study, and 15 features were collected for these patients. This is a tabular data set. And I said I was going to do unstructured data, but here's the thing. I want to be able to evaluate if the things that I'm selecting are truly important in a medical sense, not just in an optimization sense. So in this first experiment, what I want to do is use tabular data for which I do know what are the important things, convert it to language, and use my algorithm on the language version of the data so that I can compare and know if what I picked up was trash or if it was useful. So the original data looks like this. You have gender, age, education level, whether the person smokes or not, how many cigarettes, etc. And what I do is I convert this table into a paragraph. I create my own data from this so that we say the gender is, etc., age is, education level. So I'm converting the tabular data into language just so that I can do some experiments and see if my feature selection on this text is bringing up the relevant features of this table. Okay. And for the encoder function H, I'm going to be using the BioMistral large language model. So this is just a variant, just like GPT. There's other machine learning models. BioMistral is really good for healthcare data because it was pre-trained with a lot of medical language data, so it can encode the information better. And so I use this to encode this text into a fixed dimensional space. Okay. So the first thing I have here are some results regarding the sparsity level, so how many features I've selected. So first of all, on this left plot, I have the AUROC. On the right plot, I have the AUPRC. These are, if you're not familiar with it, these are two metrics of how good the model is. They're both between 0 and 1. The closer they are to 1, the better my model is. The AUROC, and the reason they're important as opposed to accuracy is that if you consider mortality prediction in a hospital, 4% of the patients die, let's say. So if I just have a very silly model that is going to predict always that the patient does not die, that model that is very silly is going to be 96% accurate. So it sounds like it's a very good model, but it's not. So these two metrics allow us to account for false positives, false negatives, true positives, true negatives. So it's a better metric than accuracy when it comes to evaluating these models. And, you know, one of these focus on true positive rate, false positive rate, the other ones on the other two. But what's important is that the baseline for AUROC is 0.5. So if you had a random model that just randomly says if the patient dies or not, it's going to achieve 0.5. So you definitely want to be above that. And the baseline for AUPRC is the occurrence rate in your data. So in this case, 15%. 15% of the patients died in this data. So presented coronary heart disease. So this is the baseline. Now on the x-axis on both plots, I have the sparsity level. So what this means is how many features have I selected so far? So this first data point is saying, using only the one most important feature that my model selected, what is the predicted accuracy? And I have basically the evolution of how that AUC is changing as I add more and more sentences in the input. So a few things to notice. Oh, sorry, I forgot to say, I have two models here, two encoding versions. Both are using the BioMistral LLM, but here's the thing. These LLMs are very expensive to be computing, to be encoding data. So one option, which is what I describe as full embedding, is every time I have a subtext of some sentences I've selected, to encode that, I actually pass it through the LLM and get the vector. Every time I do that. That's very expensive. So I also compute an average embedding in which I only compute the encoding vector for each sentence once at the beginning. And then if I want to get an encoding for a subset of 5 sentences, I average the embedding of each. So this is computationally a lot more efficient. And we can see that the performance doesn't drop too much. So for other experiments, I'm just going to be using this average embedding approach. But I want to highlight 3 things about this slide. So the first one is that about 94% of the performance that I used, if I use all my input data, can be captured using only 4 of the sentences per patient. The second thing is that if I do my average embedding approach so that I don't have to use the LLM every time, I'm getting performance that is comparable to using the LLM for every subtext. And the third point I want to make, which is just a kind of like a side effect of this, but a really cool one, I think, is that this data was tabular. And when people did feature selection with this data for tabular data, you select a subset of columns, the same subset of columns for all patients. Whereas the moment we see it as language, we can actually select 4 different sentences for each patient because there is no structure imposed on it. And this can be very useful for personalized medicine, even with structured data. The second plot that I have here is regarding an example of patients. So I have first, on the solid line, I have an example of a patient that does present coronary heart disease. And on the dotted line, I have an example of a patient who does not present coronary heart disease. And what we can see here is as we start increasing the number of sentences that we include in the model, how does the predicted probability of F change? And what we can see is that after a few iterations, the predictions sort of somewhat stabilize and stop changing. And of course, you can see here that for the patient that does die, the predictions are above a threshold, much higher than the one for people who don't die. Okay, and now the importance evaluation, right? I want to know if the sentences that I chose, I can see that they're predictive, at least empirically speaking, but I want to analyze if those sentences that were selected are medically meaningful. So what I have here is for all the data points in my test set, so just to clarify, all of these, I had training, validation, and test set. I trained the model with my trained data, and all the evaluation is with unseen out of sample data. And what I have here is for each one of the features in the original table, I'm quantifying what percentage of my unseen patients had that feature in the top 7 selected sentences. And what I wanted to here is see if what my models thought was important aligns with what is truly important. Few things to mention here. The first thing is that all the well-known important factors from the Framingham Heart Study are showing up as being selected with 100% for 100% of the patients. But there's a few other things that are relevant. So first, more granular factors are being preferred over binary counterparts. So for instance, here I have whether the patient is a current smoker or not. That is a 0-1 in the data. But the data also has the number of cigarettes that that person smokes per day. So the number of cigarettes gives more information than whether the patient smokes or not, right? It gives a lot more information. And the model is selecting this one over the binary one. Similarly, if we think of diabetes, instead of selecting whether the patient has diabetes or not, the model is selecting the sentence that describes what is the exact glucose level of that patient. So at least validating that the model is doing the right thing. And also very important, the non-relevant factors like the education level of the patient, which should have nothing to do with whether you develop coronary heart disease or not, at least not directly, is not being selected. What time did I start? Tengo 4 minutos. Okay. Okay, as easy. Okay. Okay, so something very important too with this approach is that it allows us to see what I call importance plots. So what this means is in the x-axis, I have how many sentences I've selected. On the y-axis, I have all the sentences in the data for this patient. And the color here is indicating the conditional Hello. Better? No? It's okay. We'll come back. So this is like the equivalent of the Shapley values that we have for data. here normal with no abnormal findings. Thank you. Can you hear me now? Okay. Okay, so this sentence is kind of saying there was nothing wrong with this person in the radiology report. This was selected as the most important sentence by the model, and it makes an initial predicted probability of 0.7. So saying very likely this patient won't die. The next most important sentence says no abnormal fluid are present within the pelvis. So it's kind of reiterating there's nothing wrong with this patient. So the probability goes even lower, but it's already quite close to 0. Then there is a sentence that suggests nothing is wrong, but this patient has surgical history. So for some reason, the patient had a surgery, and this is making the model increase the risk a little bit. The next sentence selected says that there's no abnormalities in any of the studied organs, and the probability basically remains unchanged. The next sentence also doesn't affect too much, pretty much doesn't change. So these first three are the ones that drove most of the change in probability. After this, they're stabilized, and they're kind of rightfully saying nothing is wrong with this patient. Now, a more interesting example, a patient who does die. So the very first sentence that is selected says that this patient has diffuse soft tissue edema, which is suggestive of anasarca. And this is a complicated condition that is making the model believe that the probability of them dying is quite high. The next sentence says they also have diffuse subcutaneous edema, meaning this patient is actually quite complicated. The probability of mortality goes even higher. And then there's this interesting sentence that says there was some limitation in the X-ray because they couldn't fully see something because there was some residue of the medication that they took. So actually, this is kind of suggesting the results are not that definitive, and the probability is going down because of that. Then it says there was no abnormal pelvic fluid. So, it's something helping saying this bad thing did not happen. It goes down even more. And then at the end, it's saying that there were some issues with the kidney that drive the prediction back up a little bit. And after this stabilizes. But I hope that you can agree with me that this is a lot more interpretable than telling a physician, this is the probability because of the notes. And so to conclude here, I'd like to mention that I think I'm very excited about these results, but there's definitely a lot of work to do to be able to deploy all of these in practice. The first one is the computational improvements. So right now I'm doing experiments with 20 sentences tops. These notes can be a lot larger. So what I want to do next is some hierarchical scaling where a note, it's split in half, I search is half, and I do kind of like a binary search to speed things up. The other thing is I'm using the LLM out of the box, just plugging it in. I could fine tune this LLM and potentially get better results. Next challenge, the multimodal data sets. I've only done experiments with language, but the same methodology can be used for video, for images, etc. And of course, real world validation. So currently I'm partnering with the child maltreatment group at NYU. The idea is that we have video and notes that clinicians have on victims of child maltreatment, families that are victims of child maltreatment, and they're in an intervention where we want to identify what are the characteristics of these patients that are leading them to drop out of this intervention. And that would ideally give us more input from the medical experts about the algorithm performance. And maybe I'll just summarize because I'm very short on time. I'll conclude saying that in this work, we have introduced this feature selection algorithm that jointly learns the prediction task as well as the selection task. It can successfully identify small subsets of 4 or 5 sentences that are predictive, almost at the same level as using the entire text. We think these improve interpretability and explainability for unstructured data machine learning models. And we hope that this at least starts to enable the application of these models in real world settings where interpretability is a must. And with that, I thank you all very much. Do we take questions maybe?
Thank you very.
Or there's no time?
Thank you. Thank you very much, Kimberly. Are there any questions or comments? Yes, please.
For this opportunity. And today, we have here some undergraduate students that may be exposed to this level of mathematical research for the first time. But still, fortunately for us, you did mention some features that are quite common in undergrad student studies that may not even be for students pursuing a career in mathematics, but even in social studies, such as the ones that I picked were the Shapley value and conditional probability. And well, at a certain point in the development of the model, it was applied to obtain the results shown. There was well, trees, of course, and some algorithm regarding sequential decision making. So for the students, for the undergrad, and for the ones who are not quite familiar with this topic, could you elaborate on those rather basic mathematics that were applied? Yes, like Shapley value.
Yeah. I think the main contribution in terms of the math part, a lot of things was not new. What was novel here and that required a little bit of math, this is very applied stuff, but it was the optimization formulation. So I would just say, if I had to summarize it, typical standard machine learning models, we have some data, we minimize a function so that we can predict that data correctly. And what I've done here is I have added a task on top of the predictive task, which is selecting the important part of the data. And I'm just modifying the function that is being minimized so that we can learn not just the task that you're interested in predicting, but also learn in the process what part of the data was most relevant for this prediction. I hope that helps.
Thank you very much. I have a question. And how sensitive are your results to the specific wording when converting table into text? Because, well, yeah.
Yes, so that's a great question. So in the first experiment, I took tables and I converted them to language. And there's a lot of ways to do that. First of all, I can say the same thing with many different ways. And I actually do have currently a paper ongoing on the study of just converting tables to language. They are very sensitive. So basically, this is not very reliable and it improves predictive performance, but it can definitely introduce a lot of errors. In this experiment, I just did it so that I could quantify the importance of a sentence because there was the tabular analog. But I'm by no means saying that that's what you should always do when you have a table. That was just for exemplifying this. The second experiment, we have real notes. So that's the main proof.
Thank you. Thank you, Kimberly, for your talk. So take this as a question, innocent question from someone that is outside of the world of machine learning. Two questions. So one general one, you mentioned some entropy minimization problem, and I noticed that the Boltzmann distribution appears somewhere there in the GIs that you mentioned, the exponential divided by the sum of the exponential. Could you explain what is the relationship between, well, entropy minimization and all what you...
Yeah, no, that's a great question. So basically in machine learning, you can prove that maximizing the likelihood of making the right prediction is equivalent to minimizing the cross entropy that you get when you have your models. So basically at the end, when I have the maximization problem that I obtain, if you put a minus and convert it to a min, that's exactly cross entropy minimization. And of course, this is all under the assumption that I'm modeling probabilities in the specific way I'm doing it. But assuming that those are the probabilities, then they're equivalent. Yeah.
I see. And I think it's related to this. So you had these encoders, H, right? Which is like a black box. It's an LLM or something like that, right? And you said that it's defined for every subset of sentences, right? S. Is there any consistency between subsets of sentences and supersets of sentences? Because you said that there was an averaging process,
Right.
was equivalent or more or less in terms
Yeah.
of performance, but maybe.
So actually, if I just take every subset and pass it through the LLM, there is no guarantee that I would have that consistency. When I do the averaging approach, there is, because all I'm doing is take whatever sentences you have in your set, take the embedding of each and average them. So there, by definition, I will have it because it's linear. So that's an added benefit of using this encoder over just the black box for everything. Yeah, great question, thank you.
I have a question. Your approach is a greedy approach. Have you tried a different optimization approach?
Yes, that's the next step. Definitely, the main reason it's greedy is because it's computationally very expensive. So if I was not gonna do it greedy, I would have to use the LLM many more times and solve the optimization problem more times. When it's greedy, I only have to do it once as I go. But something I can do, which is what I wanna do next, is introduce some stochasticity. So I can do the greedy, but then randomly go back and try to do some local adjustments because of course, this is, I could be completely stuck in a local minimum and I have no guarantee of that. However, I still think that because of the computational complexity of solving the problem for like, you know, in a more optimal way, greedy, it's still the fastest. And even that, this is not that fast. Yeah, but that it's definitely, it's for sure, you know, that's one of the biggest caveats is I'm not finding the best subset. I'm just doing conditional and greedy each time. Yeah.
The last one, is the selection model learning through importance or just approximating a soft attention mechanism? Yes, it is about the method selection or the selection method. Yeah, if it is just approximating a soft attention mechanism, a soft, sí, porque es la pregunta es si tu modelo es como lo que tratas de ver, un sí o un no, o es una aproximación de soft attention mechanisms, porque como utiliza.
Yeah, no, I'm actually not using attention at all. So the LLM that I'm using as a black box has a lot of things going on, but it has attention, it has a lot of things. But what I'm doing is I am actually given, of course, you can debate whether I'm modeling probabilities the correct way, but that's the way it's done in ML generally. You will have to debate the whole field. But assuming that you model probabilities this way, I'm deriving what max likelihood optimization would be, as opposed to just doing like the attention score or the gradient-based methods that just try to see where you're putting attention. I'm actually solving the optimization problem in that case, which is what's different from the previous works that just do gradient-based things to see where is your attention, where is the model focusing on more. Those are different. Yeah, thank you.
Okay, thank you very much, Kimberly Villalobos.
Thank you.